Hi everyone, my name is Tanish, and along with my teammate Sudhanva, we have created a project called On-Device Deepfake Detection with MobileNet V2 and post-training quantization. The main question we wanted to answer was very simple. Can a lightweight deepfake detector stay accurate after quantizing and running directly on an Android device? Deepfakes are becoming more realistic and easier to generate, so detecting them is also becoming very important. But many deepfake detectors are designed for large models to run on cloud GPUs, and that creates a lot of practical problems, such as privacy issues, latency issues, and cost issues as well. So our goal was to explore whether deepfake detection can run directly on a device. Most prior work focuses mainly on benchmark accuracies. While that is important, but it does not fully answer deployment questions. For a mobile system, we also need to know what happens after quantization. So we focused on three questions. First, how much accuracy is lost after quantization? Second, which quantization strategy works the best? And third, do all manipulation types behave the same, or are some more sensitive to compression? And this last point has also become one of our main findings. Our pipeline starts with the face forensics plus C23 dataset. We use two binary classification tasks, deepfakes versus real, neural texture versus real. And for preprocessing, we sampled 25 frames per video, detected faces using MTCNN, and resized those images to 224 by 224. And then we fine-tuned an ImageNet pre-trained MobileNet V2 model separately for both of the tasks. After training, we exported the model through PyTorch to ONNX to TF Lite. Finally, we benchmarked three quantization variants on an actual Android device to dynamic range, float 16, and int8 static.
Before quantizing anything, we wanted to confirm MobileNet V2 was a solid baseline. For deepfakes, it nearly maxes out at 98.87% accuracy. Neural textures is harder, sitting about 6 points lower at 92.4%. That gap matters because it's the same task that takes the biggest hit under int8 compression later. So when we see an accuracy drop, it's amplifying a difficulty that was already there. This slide shows real device TF Lite results. And the headline is that on-device inference is genuinely practical. All three quantization variants hit real-time speeds on a physical Android phone. Int8 was the fastest for deepfakes. Dynamic range was the fastest for neural textures, and Float 16 was consistently the slowest of the three. Accuracy stayed close to FP32 across the board, but Int8 showed the largest drop on neural textures specifically. So the takeaway isn't that one method wins everywhere. The best choice really depends on whether you're optimizing for speed, model size, or accuracy preservation. This is one of the main scientific findings. We compared the AUC drop from FP32 to Int8. For deepfakes, the AUC drop is almost negligible. For neural textures, though, the drop was around 6 times larger compared to deepfakes. So neural textures is the better stress test. It shows that subtle texture-based manipulations are more sensitive to model compression than more obvious deepfake artifacts. There are three main insights from the project. First, there is the on-device inference is practical. The real Android run reached real-time speeds across all TF Lite variants. Second, quantization preserves most of the FE32 accuracy. The deepfake task remains almost unchanged, and neural textures remains usable even though it is harder. And finally, neural textures is is the harder forensic case. It starts lower at baseline and loses more under intake compression. Our conclusion is that lightweight on-device deepfake detection is feasible, but the important lesson is that deployment-aware evaluation matters. If we only looked at FP32 accuracy, we would miss how different manipulation types respond to compression. For future work, we'd like to try quantization-aware training, more manipulation types, temporal modeling, and hardware acceleration. Thanks.